Problem F1-2 says determine the resultant internal normal force, shear force, and bending moment at point C in the beam. So as usual, the first thing we need is a free body diagram of the entire system. And of course, this free body diagram should include all external forces acting on the beam. So here I've drawn points A, B, and C, and then the dimensions. And here we are looking at a coplanar system. So we are on a 2D x and y plane. And so following this, for our reactions, we have AY and BY. And these reactions, of course, are resultant from the distributed loads. And so since we have distributed loads, we want to break them down to their resultant forces. So here we're going to have FR1 and FR2. And so for FR1 on the left, we have a 100 Newton per meter distributed load along a 1.5 meter length. So the resultant force will simply be the 100 newtons per meter times the 1.5 meters, which is of course 150 newtons. And then for FR2, we have the 200 newtons per meters times another 1.5 meters, which is 300 newtons. So I'll just write those values down on the free body diagram. And now that completes our free body diagram of the system. And now as you can see, we have two unknowns, which are AY and BY. And we need to solve for these in order to find the internal loadings. So of course, this is where we bring in global equilibrium of the system. Of course, keeping in mind that we favor a system that is stable and in equilibrium. So to find AY and BY, we can take the moments at a point with an unknown force, so either A or B. In this case, I will take my moments at point A, and I will consider counterclockwise as positive. And of course, remember that moments are taken around the z-axis, of course depending on the orientation of your coordinate system. And to find BY, we set the sum of moments equal to 0. So starting from A, we go to FR1, and from the right hand rule, this creates a clockwise moment, so that is negative. Hence, this becomes negative 150 times the distance, which here is 0.75 meters. And now moving on to FR2, this creates another clockwise moment, so this becomes negative 300 times the distance, which here is 2.25 meters. And lastly, we take the moment to BY, which creates a counterclockwise moment, so this is plus BY times the distance of 3 meters. So that completes our moment equation, and now we can simply solve for BY. So after isolating BY, we get 787.5 divided by the 3, which equals 262.5 newtons. And so that is the value of BY. And now that we know what BY is, we can now simply solve for AY by setting the sum of forces in the y direction equal to 0. And so assuming up as positive, we have AY minus the 150 newtons minus the 300 newtons and plus BY, which is 262.5 newtons. So hence AY will be equal to 187.5 newtons. So now that we have found AY and BY, we're now ready to move on to the internal loadings of the system. So of course, we want to find normal force N, shear force V, and bending moment M at point C. So that is essentially where we want to make our cut in order to analyze these internal effects. So to help visualize this, we can go ahead and make a drawing of our cut, here looking at the left side of the beam. And of course, we shall include the reaction force, AY, as well as the applied force, which is the 150 newtons. So now we can visually add in the internal loadings. So we have normal force N, shear force V, and bending moment M, just like so. Starting off with normal force, here we can set the sum of forces in the x direction equal to 0, assuming right as positive. And in this question, since there are no external forces acting in the x direction, we see that the only force in the x direction is N. And since we are analyzing at point C, I'm just going to relabel these as NC, VC, and MC. So hence, the normal force NC will simply be equal to 0. So we essentially have no normal force acting in this problem. Now we can move on to shear force, which is VC. Now, since this is acting in the vertical direction, we can set the sum of forces in the y direction equal to 0, assuming up as positive. So here we have the 187.5 newtons, and then minus 150, and then minus VC. So hence, solving for VC, we get VC equals 37.5 newtons. And so that is the shear force acting at point C. And the last thing we need is to find the bending moment at point C, which here is MC. So to find the value of MC, here we can set the sum of moments at point C equal to 0, considering counterclockwise as positive. And again here, remember that we take moments around the z-axis. And for this, of course, we need our dimensions on our diagram, which we can split to 0.75 meters from A to 150 newtons, and another 0.75 from the 150 newtons to point C. So remember, this is point C. And now taking the moments from point C to the 150 Newton force, we get a positive moment. So here we'll have, well, let's start off with MC first, which is also positive. So we get positive MC plus the 150 newtons times the distance of 0.75 meters. And the moments from point C to point A, which is negative since it's clockwise. So that is minus 187.5 newtons times the distance of 1.5 meters. So hence, after simplifying and solving for MC, MC will be equal to 168.75 Newton meters. So that is the bending moment at point C. And so now we have finally found all the resultant internal loadings for this problem.